Okay, excellent. So good morning, folks, or evening or afternoon, as the case may be. This is Vivek from Uber, and I'm going to be talking to you and giving you a glimpse into some of the work streams that we have going at Uber to support operations at our scale. Before we get into that, let me set a little context for those of you who may have joined us a little late. So Uber's mission obviously is to be a transportation platform, and we want to ignite opportunity by setting the world in motion. As of today, we operate in over 10,000 cities worldwide. Since in the last 10, 12 years, we've supported over 15 billion trips in total, of which 7 billion of them came from just 2019 alone, right? So that's some significant exponential growth there. And as will be obvious to most people, we are very data focused and data driven. And we have a bunch of very diverse teams who rely on the data platforms to support their agendas. So everything from regulatory compliance to marketing to pricing and data science and so on. And a lot of these use cases and depend on Presto at Uber. So what does Presto at Uber look like? We currently have over 12,000 monthly active users using the Presto platform, and we support about 400,000 queries every day. This translates to reading about 35 petabytes of data from HDFS every day. And we have 12 Presto clusters divided up among 2,600 actual nodes. So some pretty significant numbers up there, right? So what I'm going to do for the next 15 minutes is, instead of focusing on one particular topic and doing a deep dive on that, I'm going to give you a glimpse into multiple work streams that we currently have going at Uber to support our support operating Uber at our scale. So the first one is partial aggregation pushdown. So let's start with that, right? So the main motivation here is that we have a lot of data consistency checks, trust checks, and health checks that run on Presto at Uber. And these basically account for about 28% of all Presto traffic, right, in terms of number of queries. So the petabytes of data that we actually process it's way too expensive for us to do any kind of hashing or CRC checks on this data. So what we wind up doing is using row count or some kind of other simple aggregations on tables or table partitions as a proxy for the actual validation, right? So what we had a little light bulb moment, right? When we realized that all these Hadoop file formats, they support some kind of statistics as part of the metadata in the file's header or footer. And Presto does not use that in order to compute these aggregations. So what we do is we are building an aggregation pushdown mechanism, which is going to support using these statistics to compute the actual aggregates for some simple aggregates. So this will save time by avoiding reading the whole file and doing the initial round of aggregation. So for people what does it really look like, right? So if you take a simple query like so, where I have a bunch of simple aggregates on a table on, say, a partition column or something like that, this is a fairly contrived example, right? I've just put it there to illustrate the fact that we can do multiple aggregations like this. So we have a count star, count column, max, and min. And this query plan will be fairly familiar for people who work with the query optimizer in Presto, right, or execution engine. So we start off with a table scan at the bottom where the actual read happens from the table in HDFS. There is an initial round of aggregation, the partial aggregation, which computes the aggregates for count and max and min for the file level, and then you have the final round of aggregation after the exchange buffers, which does the final aggregation, right? So that's going to be something like sum of counts or max of maxes and things like that. So what we do here is we basically, instead of having the partial aggregation, we collapse the partial aggregation and table scan into one step, where the table scan, instead of reading the raw data from the file, it only picks up the statistics from the footer and then propagates them as the partial aggregate. So basically the output of the table scan here would have been the output of the partial aggregate step in the previous query plan. Right, so this is fairly simple. We are in the process of productionizing this. We have some numbers from our staging clusters for certain kinds of query shapes. We see significant improvement, as you can imagine, right? We have anything from 2x to 4x, but we still haven't evaluated the impact in our production traffic for these things. One simple gotcha here is that we have some processes which may not be populating these statistics in some cases, and we're still trying to figure out what the right way of gracefully handling that situation would be, right? In our case, it's fairly easy, but if you're talking about open sourcing this, then we need to figure out some way of gracefully handling that situation. So any ideas are welcome. So let me pivot and move on to the next topic. And I'm going to talk to you about approximate queries, right? So this is a well-known concept in databases where we have, and this is typically achieved by some kind of a sampling mechanism, right? Where the actual high precision of your queries is not as important in a lot of use cases, and some estimates or approximations are perfectly adequate. So the trade-off obviously is the compute resources versus accuracy of your results. And most databases achieve this by performing some kind of sampling on the data, right? So for example, we have classes of queries that do incremental development or testing, right? You're trying to converge on some kind of model or exploratory analysis. And even when you have converge on a particular model, it's perfectly okay to trade off accuracy for compute resources as long as you can contain your error within some predefined bound and so on. So in our use cases, right, what we are trying to do is we are trying to create a sampled version of the relevant data sets. And the motivation here is that we want to rewrite our queries to use these sampled data sets as opposed to the raw table data. So let me explain why this is important to us. If you consider some enormous data sets, right, like typically I'm thinking about mobile app event data or clickstream data or something like that. These are tables which contribute several billion records every day. And any kind of meaningful analysis on that using Presto is almost impossible for us, right? So the two things we want to do here is that the typical out of the box sampling techniques that we get with database engines, right? So when Presto has a couple, table sample and so on, these things don't quite work because they're not cognizant of the actual structure of the data. So if you take mobile app event data, for example, it's perfectly okay in our world to sample a 1% or a 0.1% of the entire data set, provided we have a consistent view of the whole device data, right? So if I have a billion users, I'm okay with only sampling a few thousand of them as long as I have the entire history for each of these users. So basically, I want all the UUID entries for a unique device. So getting this right using the existing sampling methods is very hard, which is why we are going with the approach of creating and maintaining ETL pipelines, which will do this sampling for us. So conceptually, this is what it is going to look like, right? Like a query coming in with some session parameter set, which will let you know that using sample data sets is okay. We would rewrite the query within Presto using a config service which has this mapping, right? Basically between the sample data sets and the raw data sets, and then execute the query on Presto on the sample data sets. In addition to doing a simple query rewrite with table name replaced, we are also planning on maintaining statistics on the actual sampled process, right? So this way we can have, there are some simple case would be like if you have a count star query coming in, if you have the sampling percentage, now you know what the actual count star would be, right? So, but if you extrapolate this to a few other cases where you can have uh, where you can have, sorry, if you extrapolate this to a few other cases where you can actually propagate your error bounds across join boundaries or some other kinds of aggregations, this would certainly help with maintaining and providing a richer class of queries and better estimates for various use cases. So this work is still in its early stages, and we have some ideas. If there are people who are interested or you have experienced something like this before, again, please reach out to us. We would be happy to have conversations with these. So a final pivot, I'm going to talk to you a little bit about our experiences with the Java virtual machine and memory management that we spent a lot of time on this past year. So as with most database systems, high-performing database systems, right? Presto performs very well, and all these things perform very well as long as you remain within the boundaries of certain things, right? So the moment you step over the boundaries of good performance, then you fall off the proverbial cliff. And so this started happening at Uber consistently last year, right? We started having a lot of these long garbage collection pauses. These were the old generation stop the world garbage collection process where everything gets frozen up. None of the jobs are able to make progress. There is a drop in throughput. And this is obviously leading to variable performance, flaky performance, and it was an operational nightmare, right? There were outages and all kinds of things. In the short, anecdotally, right, in the short term, what we did was we had a script we had some bunch of scripts which would go and look at the JVM logs, parse them, try to identify when a long GC was happening, and then bounce the process, basically kill it and restart it. But obviously this was a less than desirable solution. We didn't like it. Our customers were not very happy. They're not very happy about that either. So a fair amount of research later, what we realized was that there was a simple win we got by just upgrading our JDK from 8 to 11. So Presto team at Uber is one of the first teams that actually did this upgrade from 8 to 11. And this led to a significant improvement, right? We started seeing our peak GC pauses go from 20 minutes or tens of minutes to 8 or 10 seconds at the most, right? This was pretty big. This also contributed to much increased CPU throughput. The main credit here goes to the parallelization of the full GC in the there's a G1 algorithm that does the parallelization of the full GC, which is I think available from Java 10 onwards. And there's a link there to this if you're interested in learning more about this. So anybody in the community who's encountering something like that, we would recommend upgrading your JDK. The second thing that we discovered in our analysis, right, was that there was a lot of memory pressure being put on due to the Parquet reader itself, right? So most of our data sets are in Parquet and Uber, in case I didn't mention that before. So the Parquet reader, there was a lot of large object allocation happening in Parquet. So if you can see this list here, right, it's basically showing you how the allocation of humongous regions happens in the JVM. And this mainly is from two reasons, right? It starts off, there are two parameters which control how, or which are supposed to control how memory is allocated when you read data from Parquet files. One of them is that the Parquet reader reads data in column chunks. And these were both, so reading in column chunks and reading in terms of blocks, both of these things were actually pre-configured in Presto, right? As in they were not configurable in Presto. They were predetermined. So what we did was we realized that there was an open source patch which allows dynamic sizing for blocks. So this was previously set to 1024, hard coded to 1024, and well, it seems like a reasonable estimate in most cases, if you have any kinds of complex data types in the row, like embedded structures and so on, this 1024 can still be a pretty big number for certain use cases, right? And this winds up adding a lot of allocation to the, this leads to large memory allocations. The second thing was Presto was reading data in column chunks, and that was the lowest atomic value that you were reading. And changing this reader to consume it one page at a time is another project that we have in progress to reduce the pressure on memory from Parquet reader. So these two things are still not yet in production. We are going to go push it to production, and we will have results on these soon. So this is about all I had for today. If we have a few minutes, I will take some questions.
This is Amit here. You have about like 3 or so minutes. If you find a question in the Q&A panel that's relevant to what you just talked, then you can just read it out and answer that. Otherwise, you can take it offline, go through the questions, and we can have Rong actually come and present our session now.
Sounds good. I think I have a couple of questions here from Alexei. So he asks, does partial aggregations work with Hoodie? So in our world, we use Presto with Hoodie, right? And he also has a follow-up question: do you use Presto with Hoodie? We use Presto with Hoodie. The file formats are different, right? So I think what we are thinking about in terms of statistics is for us to make this work for Parquet and ORC. And for Hoodie, there is a separate project where we are going to be we are planning on supporting full-fledged statistics across tables, right? Not just in terms of files or partitions. So there is a project on our plate where we will be hooking Presto up with full Hoodie statistics.